Welcome to the deep dive. Glad you could join us. Today, we're really getting into something fundamental waves. Specifically, we're tackling Lab 3, standing waves on strings. Okay, let's unpack this. Our mission for you, listener, is simple. Really get this lab. We're talking core concepts, the actual procedure, how to handle the data, and yeah, feeling totally ready for any pre-lab quiz stuff. By the end of this, you should feel confident walking into that lab.
Absolutely. And what's fascinating here is how foundational this lab is. I mean, for understanding wave phenomena everywhere, the objective is pretty neat, actually. We want to, demonstrate these standing waves visually, think like a guitar string vibrating. And then, crucially, we verify that key formula connecting wave speed to the string's tension and its mass per unit length. It's a really core experiment. Shows how observation and physics theory just click together.
Nicely put. Okay, so let's dive straight into the core theory then. Standing waves, what are they? Well, imagine a string, right? Fixed at both ends. When it vibrates, it doesn't just wiggle randomly. It settles into these specific stable patterns. It's normal modes.
Right, normal modes. It's like the string finds its preferred ways to vibrate. And you see these points called nodes. Points where the string looks completely still, even while the parts in between are moving a lot. Like plucking a guitar string, you sort of see that shape.
Yeah, that's a great way to picture it. And these normal modes, they depend on the energy you put in, like how hard you pluck it. The visuals in the source material show the first three modes really well. Mode 1, N1, is just one big loop, no nodes in the middle.
Just at the ends where it's fixed.
Exactly. Then N2, you clearly see one node right in the center, two loops. And NN3, two nodes inside, making three loops. You can visually track how it gets, well, more complex as N increases.
It's like the string's folding itself into more segments.
Sort of, yeah. Different ways of resonating in that fixed length.
Okay, and here's where it gets really interesting, I think. The math behind it. There's this neat relationship between the wavelength that's lambda, F, and the string length, L. The formula is N to Ln, where N is just an integer, right? 1, 2, 3.
That's the one. And N tells you the mode number, like how many loops you see.
Precisely. It directly corresponds to the number of loops or antinodes you observe.
So for N1, that first big loop, the wavelength is actually twice the string length.
Correct.
N2L.
And for N2, two loops, the wavelength is exactly the string length.
At Wheeze L.
Yep. It's elegant because it directly incorporates those fixed ends, the boundary conditions.
Yeah. Okay, so how does that connect to the bigger picture, like wave speed?
Right. If we connect this to the bigger picture, this wavelength is key to finding the wave speed round phase. And we've got two main ways to calculate V in this lab. That's kind of the point to compare them. First, the experimental way.
Vex P of phi.
Frequency times wavelength.
Exactly. And F, the frequency is given. It's fixed by the motor vibrating the string, 120 hertz in this case.
Okay, so F is constant. We measure or calculate A based on L and N, and boom, we get Vex.
That's the idea. That's the velocity based on the wave's observed behavior, how fast it's oscillating and how long its pattern is. Then there's the second way, the theoretical one, V fix S well, AT. Square root of T over mu. Okay, what are T and mu again?
Good question. T is the tension in the string. You control that by hanging weights, masses off the end. More mass, more tension.
Got it.
And mu, that's linear density or mass per unit length. Basically, how heavy the string is for its size. Like, is it a thin fishing line or a thick rope?
Okay, so one velocity from frequency and wavelength, the other from tension and how thick the string is.
Exactly. And the goal is to show that Vex and Vth are ideally very close. It demonstrates the physics holds up.
All right, theory makes sense. Let's talk practicalities. The lab setup, you've got the string, one end hooked to a motor.
That 120 hertz vibrator.
Right. Then it goes across over a little pulley.
Uh-huh.
Then masses hang off the end. That's what creates the tension T. Now, you mentioned the length L from the motor to the pulley. That needs to be measured carefully, right? And shouldn't be more than 60 centimeters.
Correct. On both counts. Measure it accurately.
And crucially, don't change it. Once you set L, it stays the same for the whole experiment.
Yes. That's super important. I mean, think about it. If L changes, your wavelengths all change.
Ah, right. Your calculations for L would be wrong for modes you measured earlier?
Exactly. It ruins the consistency. Keep L constant.
Okay, so let's pin down the variables. What's changing? What stays the same?
Good idea. The independent variable, what you actively change, is the hanging mass, M, because that changes the tension, T.
Okay, I control the mass.
The dependent variable, what you observe as a result, is the standing wave pattern that forms, specifically which mode number N you get and its wavelength.
So I change the mass, and I watch for which pattern N1, 2, 3 appears.
Precisely. And the constants, the things you must keep the same.
Okay, let's see. The frequency, F, is fixed at 120 hertz.
Yep.
The gravitational acceleration, G, we use 9.80 meters south.
Standard value, right.
That string length, L, once we set it.
Crucial.
And, oh, the string itself doesn't change, so its mass per unit length, it should be constant too.
Perfect. Keeping those constant is key to a fair comparison.
So the actual process, we hang masses to get the different modes, N1 up to N5. You mentioned something interesting. The first mode, N1, needs the most weight.
Generally, yes. To get that single large amplitude loop stable often requires the highest tension.
And then for N2, N3, you need less weight.
Correct. As N increases, the tension required to achieve resonance at that fixed frequency usually decreases.
Huh, okay. And the goal is always to get the biggest, clearest wave pattern possible for each mode?
Yes. Try to maximize the amplitude. It just makes it easier to see the nodes and confirm you've really hit the right mode. It takes a bit of fine-tuning with the mass.
Right, fiddling with the weights a bit.
Exactly. Now, before you even start that, you need to measure WIL, the mass per unit length.
Okay, and how do we do that? Do I take the string off the setup?
No, definitely not. The instructions are clear. Use a separate piece of the same type of string.
Ah, okay. Like a spare piece.
Right. You take that spare piece, measure its total mass on a balance.
Got it. Use the scale.
And measure its total length carefully with a ruler or meter stick.
Okay. Mass and length.
Mass is just mass divided by length. Definitely mellow.
Simple enough.
But here's the critical part.
Yeah.
Units. If you measure mass in grams and length in centimeters.
Which is pretty common on lab balances and rulers.
Exactly. You must convert them. Mass needs to be in kilograms and length needs to be in meters.
So divide grams by 1,000 and centimeters by 100.
Yes. So your final is in kilograms per meter, kg. If you don't do this, all your VIF calculations later will be way off because T will be in newtons, which uses kg, but nu won't match.
Unit consistency. Got it.
Sure.
Super important.
It really is. Easy points to lose if you forget.
Okay, so is measured and converted. We've found our 5 modes by adjusting the mass for each n. Now we crunch the numbers. So for each mode, n will 1 to 5. I need a row in my data table. What goes in it?
Right. First column, the mode number n.
1, 2, 3, 4, 5. Easy.
Second, the total hanging mass, m, that produced that mode. Make sure it's in kilograms.
Well, convert if needed.
Okay. Third, calculate the wavelength for that mode using equals 2ln. L is your constant measured length in meters, so U will be in meters.
Equals 2ln. Got it.
Fourth, calculate the experimental velocity, Vex. That's Vex, P-L-E-V. Use F equals 120 hertz, and all you just calculated. Velocity will be in amps.
Vex P check.
Fifth, calculate the tension, T. That's T equals mg. Use M in KOG, and G equals 9.80 meles quotantas. Tension is in newtons.
TMG. Okay.
And finally, sixth, calculate the theoretical velocity, Vex.
Yeah.
That's Vet squared. Use the T you just found in the F you measured earlier in kg. This velocity is also in MEF.
Ves E squared. Wow. Okay, so 6 columns for each of the 5 modes.
Yep. It lays everything out clearly.
And then the grand finale, comparing Vex and VAF.
Exactly. You calculate the percent difference for each mode. It shows how well your two methods agree.
Is there a specific formula for that? It's not just percent error, right?
Right, because neither Vex nor Vith is necessarily a true or accepted value here. Both come from measurements. So we use percent difference. The formula is the absolute value of Vex
Okay, the difference between them.
divided by the average of Vex and Vith.
Divide by Vex plus VIF too.
Precisely. And then multiply the whole thing by 100 to get a percentage.
So percent diff Vex plus def 2, 100.
That's the one. It gives a fair comparison when both values have some experimental uncertainty. What's fascinating here is you're directly testing a physical model with your own measurements.
Yeah, that's cool. See how close you get.
Exactly.
Okay, that covers the lab procedure and analysis pretty thoroughly. Now, what about getting ready for those pre-lab quizzes? How do we consolidate all this?
Great question. It's about making sure the key ideas are solid in your mind. So based on this lab, here's what you should focus on. 1. Definitions. Really know them. What is a standing wave? What are nodes? Be able to define wavelength, frequency F, tension T, and mass per unit length wave.
Just knowing the terms.
Knowing what they mean, yeah. 2. Formulas. Be ready to recall and use the main 3. Vex BLN, Vex Pedo E, and VGT. Know what each letter stands for and the units.
Like, could they ask you to rearrange one?
Possibly. Or just apply given some values. 3. Procedure comprehension. Understand the how and why. How do you set it up? How do you measure UTR correctly? Including the unit conversion, why keep L constant?
The practical steps.
And the reasoning behind them. 4. Relationships. Think about cause and effect. If I increase the mass tension, what happens to the pattern N? How do E, F, and V relate? If F is constant, what happens to V if E, O changes?
Thinking connections.
Right. 5. Purpose of calculations. Why calculate both velocities? What does the percent difference tell you? Is a small difference good? What might a large difference indicate?
Understanding the point of the math.
Exactly. And finally, 6. Some critical thinking. Often they pull from discussion questions, like which velocity, vext or vth, might be more accurate in reality and why?
That's interesting. Why would they differ?
Well, that raises an important question.
Hmm.
Think about sources of error. Is the string perfectly uniform? Probably not, so it might vary slightly.
Okay, so VIF might be slightly off.
Could be. Is there friction in the pulley? That means the actual tension T might be a bit less than mg.
Ah, another hit to VIF. What about VEX?
For vext, a flum is the frequency exactly 120 hertz. Maybe slight motor fluctuations. And how accurately can you judge where the nodes are to determine N and thus LOM? Seeing stationary nodes can be tricky.
Right, getting up perfectly depends on judging N and measuring L. So both VEXP and VIF have potential small errors.
Precisely. Understanding those potential errors is key to critically evaluating your results, and often fair game for quizzes.
That's a fantastic prep list. Okay, what a dive into Lab 3. We've gone from the basics of standing waves and
If
nodes
there's more in the mode,
to the 2 ways to calculate wave speed, the whole setup, the data crunching, and now quiz prep. I think you, our listener, should have a really solid handle on this now. You're ready for the lab.
definitely. And just as a final thought, if we connect this to the bigger picture, remember these standing wave principles aren't just for lab strings.
Right, you mentioned musical instruments earlier.
Exactly. Guitars, violins, pianos, wind instruments, they all work by setting up specific standing waves. But think broader, too. Earthquake analysis uses seismic standing waves bouncing around inside the Earth.
Wow, really?
Yeah. And even in quantum mechanics, the electrons in atoms exist in states that are essentially standing wave probability distributions.
That's mind-bending. So the simple string experiment.
It taps into fundamental wave behaviors seen across vastly different scales and systems. How might these simple rules play out in ways we can't even see? Something to think about.
Absolutely fascinating. Well, thank you for joining us on this deep dive. Keep exploring, keep asking questions. We'll catch you next time.